Swayam Prabha. Digital India. Educated India.
So, now we will start the topic Introduction to Feedback Control. We will discuss the topic Introduction to Feedback Control. Fine. Now, before discussing the feedback control schemes, we will develop the block diagram for a closed loop process. Before discussing the different feedback control schemes, we will develop the block diagram of a closed loop system. So, development of block diagram. Development of block diagram of a closed loop process. Closed loop process. We have developed the block diagram for open loop process. So, now we wish to develop the block diagram of closed loop process. For this purpose, we will consider one example, that is heating tank system. For the development of block diagram, we consider the heating tank system. Steam is introduced through this coil with a flow rate of FST. Input flow rate is Fi and temperature is Ti. Outlet stream is going out at the flow rate of F and temperature T. Fine. Now, what is the control objective? Control objective is to maintain the temperature at its desired value. The control objective of this example process is to maintain the temperature at its desired set point value, and we are assuming that Fi and F, they are identical and they are constant quantities. We are assuming that Fi and F both are identical and they are constant. So, what is the controlled variable, what is the manipulated variable, and what is the load variable, that we can detect Now, control variable is temperature. What is the manipulated variable? Corresponding manipulated variable is steam flow rate and load variable is Ti. Fine. Now, this is the schematic of an open loop system. This is the schematic of the open loop heating tank system. Fine. Now, we have assumed that the inlet and outlet flow rates are identical and they are also constant. It indicates there is no variation of height. It indicates height is also constant. Fine. Now, we will configure the controller around this process. We have already detected the control variable, manipulated variable and load variable. Now, we will configure the feedback control scheme for maintaining the liquid temperature. So, this is the heating tank system we considered as an example. Fine. Now, first we need to measure the temperature by using a measuring device. We need to measure the temperature using a measuring device. So, this is the block for temperature sensor which is employed to measure the liquid temperature. Now, this measured temperature usually differs from the original temperature value. This measured temperature we can represent by T suffix m. In the next step, this measured temperature is compared with its set point value represented by TSP. So, this is positive and this is negative. Then the output of this comparator is can be represented by epsilon, where epsilon is equal to set point temperature minus measured temperature. The comparator output can be represented by epsilon, where epsilon is equal to TSP minus Tm. Then this information is supplied to the controller. This information is supplied to the controller. Based on the error signal, the controller takes action, and that action is physically implemented through this control valve. The controller action is physically implemented through the final control element, that is control valve. Fine. This is the configuration of the controller employed around this heating tank system, and this is the schematic of the closed loop heating tank system. This is the schematic of the closed loop heating tank system or closed loop process. by the introduction of the controller the loop is closed. Fine. Now, in the next we wish to develop the block diagram for this closed loop process. In the next we wish to develop the block diagram for this closed loop process. So, we will consider a block for a process. This block is representing the process. Input to this process is suppose m bar s. Input to the process is represented by m bar s, that is nothing but the final control element output. Fine. And another input is considered, that is the disturbance d bar s. So, there are two inputs affecting the process. One is the final control element output, another one is the disturbance. Fine. Disturbance is represented by d and final control element is represented by here m. The output of the process is y. In Laplace domain we can write y bar s. Fine. This is the open loop process. This is the block diagram of the open loop process. There is no controller involved with this open loop process. Now, what we are doing first? We are first measuring the temperature using a measuring device. So, one block we can draw for the measuring device. This measuring device is measuring the temperature. Basically, this y is T only. Fine. The control variable y is here the temperature of the liquid in the tank. So, first we are measuring the temperature using this measuring device. What is the output of this measuring device? Output is y suffix m, that is nothing but measured temperature. Sensor output is measured temperature Tm. Fine. Now, this measured temperature, this measured signal, measurement signal goes to the comparator and the sign is negative. You just compare the configuration with this block diagram. Now, another input to this comparator is y set point, that is y suffix sp, and we use positive sign for this. So, there are two input signals considered for the comparator. What is the comparator output? Epsilon. In Laplace domain we can write epsilon bar. This comparator output is supplied to the controller. So, one block we can draw for the controller. The error signal epsilon goes to the controller. Then the controller calculates the control action. We can represent the controller output by C, and in Laplace domain C bar. This controller output goes to the final control element, that is the control valve. the controller output C is supplied to the controller output C goes to the final control element, and the final control element output is M. So, this is the block diagram of the closed loop process. Fine. This is the process which has two inputs. One is the final control element output and another one is the disturbance. These two inputs affect the process. If we consider the liquid tank system, heating tank system, then the output is the temperature. This temperature is first measured by using one measuring sensor. Sensor output is T suffix m, that is measured temperature. Then that measured temperature is compared with its set point value. Comparator output is represented here by epsilon. That information goes to the controller, and using that information controller calculates the control action. Then the control action is physically implemented through this final control element. So, this is a closed loop block diagram of a process. Fine. Next, we will discuss different types of controllers. Different types of controllers. Now, if we redraw the controller block, then we see that input is m bar s, output is input is epsilon bar s and output is C bar s. So, basically the controller relates C to epsilon. So, various types of controllers differ in the way they relate C to epsilon. Various types of controllers differ in the way they relate C to epsilon. So, first we will consider three types of controllers which are classical controllers and which are definitely feedback controllers. These three controllers are proportional controller. This is also called, this is also named as P only controller. Second controller is proportional integral controller. Proportional integral controller, which we can call as PI controller, proportional integral. Proportional integral controller additionally includes the integral term. Third controller is proportional integral derivative controller. Proportional integral derivative controller, which we can call as PID controller. Fine. These are the basic feedback controllers and we will discuss one by one. So, first we will consider proportional controller. First we will discuss proportional or P only controller. The controller output C, which can be written in terms of deviation variables as C prime t, is proportional to the error signal. If we see the control block, we observe that epsilon t is the input and Ct is the output. Fine. Now, we have written here C in terms of deviation variables. So, C prime t is proportional to the error signal, that is the input to the controller, and that is why the name, I mean that is why it is called proportional controller. So, we can write this again as C prime t equals Kc epsilon t. Fine. And finally, we write Ct equals Cs plus Kc epsilon t, where C prime t is equal to Ct minus Cs. I have mentioned that C prime is the deviation variable. So, C prime t we can write as Ct minus Cs. Now, Kc is the proportional gain of the controller. Kc is the proportional gain of the controller. It is very obvious, you see Kc we can write as C prime t divided by epsilon t. Can we write this? Kc is equal to C prime t divided by epsilon t. You just see this block, Ct is the output, epsilon t is the input. I have mentioned earlier that gain is the change in output per unit change in input. It is obvious from this in this correlation. So, we can say Kc as the proportional gain. Now, what is Cs? Cs is the bias signal, controller's bias signal. We can define it as Cs is the controller output when there is no error. If you see this equation, we can write that Ct is equal to Cs when the error is 0. So, bias signal is the controller output when error equals 0. Fine. This Kc is one tuning parameter, controller tuning parameter. The value of that parameter we need to determine. So, one equivalent term is also used in different softwares and industrial practice, that is proportional band. One equivalent term of Kc called proportional band is also used in different flow sheet simulator and in industrial practice. proportional band which is 100 divided by Kc. Proportional band is 100 divided by Kc. Now we wish to determine the transfer function of the controller. You see, for the P only controller we got C prime t is equal to Kc epsilon t. Fine. Now if we take the Laplace transform of this, then we obtain C prime bar s equals Kc epsilon s. If we take Laplace transform, we obtain C prime bar s is equal to Kc epsilon s. Now what is the output of the controller? C prime bar s. What is the input to the controller? Epsilon s, and this can be represented as transfer function of the controller, GCS, and GCS is equal to Kc. So for PI controller the transfer function is, for P only controller the transfer function is equal to Kc. Fine. Now we will conclude the P only controller. With the increase of Kc, the controller becomes more sensitive to error. This is the first conclusion which we can draw for the P only controller. With the increase of Kc, the controller becomes more sensitive to error, epsilon. Fine. If we increase the Kc value, the controller becomes more sensitive to epsilon. Now we want to see the behavior of P only controller. How the controller behaves, that we want to represent graphically. So remember the controller equation, that is Ct equals Cs plus Kc epsilon t. This is the P only controller equation in time domain. Fine. Now if we plot C versus epsilon, we obtain the Cs when epsilon is equal to 0. So this point is representing Cs, because we know that Ct equals to Cs when epsilon is equal to 0. So we are considering this where epsilon is equal to 0. So the corresponding C value is Cs, and when we increase epsilon, it increases like this with a slope of Kc. So slope is Kc. Fine. And the last value of C is C max, maximum value of C. We cannot consider C as infinity. due to the some physical limitation of final control element, we have to put constraints on C. So, the higher limit is C max and lower limit is C min. Now, this variation is obtained when epsilon is positive, when epsilon is positive. Similarly, we obtain this line when epsilon is negative, and the minimum value of C is C min. Fine. So, this is the second conclusion on P only controller. Next, we will discuss how the controller responds with a step change in error signal. So, we will use the controller equation in Laplace domain. This is the P only controller equation in Laplace domain. Now, we will consider a unit step change. We will consider a unit step change in error signal. Then the controller equation yields C bar prime S is equal to Kc by S. Now, if we take inverse of Laplace transform, then we get C prime t equals Kc. If we take inverse of Laplace transform, we obtain C prime t equals Kc. That means Ct is equal to Cs plus Kc. Fine. Finally, we get Ct equals Cs plus Kc. Now, we will produce the plot to represent this concept. This is time t and this is Ct. Now, initially the process was initially the controller has the value of Cs. Now, we are introducing a unit step change at time t equals 0. Then the controller output provides the value of Cs plus Kc. Fine. So, this is the controller behavior against a unit step change in error signal. Okay, next we will discuss the second controller, that is PI controller, proportional integral controller. Next we will discuss proportional integral controller. Fine. Ct equals Cs plus Kc epsilon t. This is the representation of P only controller. Ct equals Cs plus Kc epsilon t. This is the representation of P only controller. Now, additionally we need to include the integral term with P only controller to obtain PI controller. That integral term is represented by Kc divided by tau I integration of error t dt. So, this is the integral action and this is the proportional action. Combining these two actions, we obtain PI controller. Fine. Now, we can represent this equation in terms of deviation variables for finding the transfer function of PI controller. Accordingly, we can write C prime t equals Kc epsilon t plus Kc divided by tau I integration of error t dt. By taking Laplace transform and rearranging, we obtain the transfer function as GCS equals C bar prime S divided by epsilon bar S equals Kc 1 plus 1 divided by tau is. By taking Laplace transform and rearranging, finally we obtain the transfer function of PI controller as GCS equals Kc multiplied by 1 plus 1 divided by tau is. This is the transfer function of PI controller. Fine. Now, we will make some remarks on this PI controller. The integral action eliminates the offset. First conclusion is the integral action eliminates the offset. Offset is the steady state error. Offset is basically the steady state error. If we plot y versus time t, we may get this type of response under a controller. This is the set point value and the value which we are getting finally, that is the steady state value. So, this corresponding value, this value is the steady state value, y steady state. Now, the difference between the set point value and the steady state value is called offset. The difference between the set point value and the steady state value is called as offset. So, offset is basically y set point minus y steady state. Now, this PI controller can eliminate the offset due to the inclusion of integral action. I mean, the P only controller cannot eliminate offset. Fine, this is the first conclusion. Now, due to the addition of integral action, the overall response becomes more sluggish. This is the second conclusion. due to the addition of integral action, the overall response becomes more sluggish due to the increase of order by 1. Due to the inclusion of integral action, the overall response becomes more sluggish. Say for example, if we consider a first order system, and if we employ a PI controller, then the overall system becomes second order system. If we consider a first order system and if a controller is employed, then the overall response becomes second order dynamics. That means order is increased by 1. Now, in a plot, we have compared the dynamics of first order, second order and fourth order systems, and we have observed that increasing the number of capacities in series increases the sluggishness. So, by that line we can say that by the inclusion of integral action, the order is increased by 1. It means the overall response becomes more sluggish. Fine. So, this is the second conclusion. Now, we will consider a unit step change in error signal and we will observe the response of PI controller. So, PI controller equation in Laplace domain we can write as C bar prime S equals epsilon S multiplied by Kc 1 plus 1 divided by tau is. Can we write this, the PI controller in Laplace domain? Now, we will consider a unit step change in error signal. We will consider a unit step change in error signal. That means epsilon bar S equals 1 by S. Then we obtain C bar prime S equals Kc divided by S plus Kc divided by tau y 1 by A square. Fine. Now, inverting this we obtain C prime t equals Kc plus Kc divided by tau y multiplied by t. Taking inverse of Laplace transform, we obtain finally C prime t equals Kc plus Kc divided by tau y multiplied by t. Now, we will represent this graphically. This is time t, this is Ct. Now, at time t equals 0, the controller has the value of Cs, and we are introducing a unit step change at time t equals 0. Accordingly, the controller output becomes Cs plus Kc. Fine. So, Cs plus Kc we can obtain from this Cs plus Kc plus Kc divided by tau y into t. So, it is obvious that at time t equals 0, Ct equals to Cs plus Kc, and when time is greater than 0, the C increases linearly with a slope of Kc divided by tau I. Slope equals Kc divided by tau I. Fine. This is the behavior of PI controller against a unit step change in error signal, and that error signal, the change in error signal is introduced at time t equals 0. Now, this integral action we can write as Kc divided by tau I epsilon t dt. Fine. Kc is the proportional gain and tau I is the integral time constant. One additional tuning parameter is there, that is tau I, and tau I is called as integral time constant. It is also called as reset time. Unit of tau I is time. Fine. Now, for the PI controller, we got C prime t equals Kc plus Kc divided by tau I into t. By introducing a unit step change in error signal, we obtain for PI controller C prime t equals Kc plus Kc divided by tau I into t. Now, if we consider t equals tau I, the controller output yields C prime t equals Kc plus Kc. So, this term is yielding Kc. Understood or not? For the PI controller, one additional term is there, that is integral action. The integral action can be represented by this form: integral action equals Kc divided by tau I integration of error t dt. Now, the tuning parameter Kc is present also for P only controller. Now, the additional term tau I is present with this PI controller. That tau I is called integral time constant or reset time. The unit of this integral time constant is time. Fine. Now, we obtain this form C prime t equals Kc plus Kc divided by tau I into t, considering a unit step change in error signal. This form we obtain. Now, we are just considering time t equals tau I. Then the controller output yields C prime t equals 2 Kc. Can we define now the reset time? What is reset time? Reset time is the time required for the controller. Reset time is the time required by the controller to repeat the initial proportional action change. Initial proportional action change in its output. You see that initially we had one proportional gain, that is Kc. Now, due to the addition of the integral term and considering time equals tau I, we are getting another proportional action, and therefore we can say that the reset time is the time required by the controller to repeat the initial proportional action change in its output. Okay, fine, thank you.